Imagine stepping onto a construction site, but instead of, the usual chaos of hammers and saws, you just hear this hum, a giant machine.
Right?
And right there, a house is actually rising up, layer by layer. No bricks, no hands laying them, just this robotic arm extruding material.
It really does look like something out of science fiction, doesn't it? Like a sculpture emerging, but, well, you can live in it.
Exactly. And it sounds futuristic, but it's actually happening right now. People are building homes this way.
It's genuinely starting to reshape how we think about construction.
Welcome to the deep dive. This is where we take your curiosity, grab a whole stack of sources, research papers, industry reports, you name it, and really try to figure out the real story behind these big, flashy topics.
And today we're diving into something that's definitely caught people's imagination. 3D printing a house.
Yeah, we want to take a really grounded look. Is this just like a cool gimmick, a niche thing for maybe a few high-tech projects, or is it something more? Is it, the actual future foundation for how we build houses?
That's the core question, isn't it? Is it novelty or revolution?
So our mission today is to get past those slick viral videos you see online. We want to really dissect the actual process, look at the tech involved, the materials, which sound pretty unique.
They are, and we need to talk about the benefits, of course, what's driving all this excitement, but just as importantly, the hurdles, the big challenges that are still, frankly, standing in the way.
Right. So by the end of this, you, our listener, should have a much clearer picture. Is this tech really on track to become standard practice, or are the obstacles still too big?
Think about it, a faster way to build, more efficient, maybe even creating shapes and forms we haven't really seen before in housing because they were just too expensive or complicated.
But okay, how does it really work? From the computer file to, a place someone can actually live in.
Yeah.
And what are those hidden challenges, the things they don't always mention in the press release?
Exactly. We're going to unpack all of that. The tech, the regulatory stuff, the real-world complexities.
Let's get into it. Okay, so you mentioned this idea of digital fabrication earlier. Our sources are calling it a core concept, even a third digital revolution. What makes it so revolutionary compared to, say, just designing on a computer?
Well, think about the first couple of digital revolutions. They let us use digital information, the bits, to influence the physical world, the atoms, but sort of indirectly.
Like designing a car part on a computer, then someone makes it.
Exactly. You design the blueprint, the bits. Then a human builder, or traditional machine, interprets that blueprint to make the physical thing, the atoms. There's always that translation step, manual labor, interpretation, craft.
Right.
But this third digital revolution, as our source designing reality frames it, is about letting those bits directly change the atoms. The digital design interface basically controls the physical construction immediately.
Okay. Cutting out the middleman, in a way.
Precisely. It fundamentally changes how the physical world gets built. Architects, designers, builders, they can almost program the physical structure, turning these incredibly detailed digital plans into real things with a speed and accuracy that just bypasses centuries of traditional methods. It's a total rethink.
So, closing that gap between idea and reality. And 3D printing uses this additive principle, you said. How's that different?
Yeah, additives is the key word here. Traditional construction, if you think about it, is often subtractive. You start with more material, then you need like a big block of stone or wood, and you cut away, carve out, remove the bits you don't want.
Like a sculptor.
Exactly like a sculptor. Additive is the opposite. You build up the object layer by tiny layer, putting material only where the design says it needs to be.
So no waste from carving things away.
Minimal waste, ideally. Instead of cutting away excess, you're adding only what's essential. And that difference, it's huge. It affects material use, the kinds of shapes you can make, how you manage resources, everything. It's like building with Lego bricks, but with concrete, guided by a super precise digital plan.
That makes a lot of sense. Less waste sounds great.
Yeah.
But let's get real about what this looks like for building a house. Because those videos sometimes show a whole finished house appearing.
Right, and that's where we need to manage expectations immediately. It's really crucial. Most systems, and this is clear from our sources and what's happening on the ground, print only the concrete wall shells.
Just the walls.
Mostly, yes.
Wow.
The structural concrete walls, exterior, sometimes interior load-bearing ones, the 3D printer makes those, but, and this is the key part, the rest of the construction's still requiring traditional methods.
So you still need roofers, electricians, plumbers.
Absolutely. The roof structure, windows, doors, wiring, plumbing, insulation, drywall, paint, finishes. All that stuff is typically done the old-fashioned way. by skilled tradespeople, it's more of a hybrid process right now, a mix of automation and traditional craft. Not a magic box spitting out a finished home.
Okay, that's a much clearer picture. So it's the structure, primarily. And how do these printers actually work on site? Are there different kinds?
Yeah, generally you see two main types in action. First, there are the gantry-based printers. These things are usually huge, like massive overhead cranes or plotters that span the entire building footprint.
Like a giant Siazi moving back and forth.
Exactly. They move along rails, depositing the material layer by layer. They're very stable, very precise, especially for larger, more straightforward rectangular or square designs. Think of a giant inkjet printer, but squirting out concrete.
Okay. And the other type?
The other main type uses robotic arms. These look more like the big articulated arms you see in car factories, but obviously scaled up and adapted for construction.
More flexible, maybe.
Generally, yes. They often have a wider range of motion, can be mounted on tracks or even mobile bases. This makes them potentially better for more complex shapes, curves, reaching tricky spots that a rigid gantry might struggle with. So you've got scale and stability with gantries versus flexibility and intricate geometry with robotic arms. Each has its place.
Got it. And the stuff they're printing with, the ink, so to speak. It's not just regular concrete you pick up at the store, right?
Yo, absolutely not. This is a whole area of specialized material science. You need these specialized concrete mixes, specifically engineered, tailored for 3D printing.
Why? What's different?
Well, think about traditional concrete. You pour it into a form, like a wooden mold for a beam, and it sits there and cures. Or no, it has time.
Yeah.
3D printed concrete doesn't have that luxury. It needs to be fluid enough to get pushed smoothly through a nozzle, like toothpaste. But the moment it comes out, it has to be stiff enough to hold its own shape and support the weight of the next layer being put on top almost immediately, without slumping or collapsing.
Wow. That's a tricky balance. Flowing 1 second, solid the next.
It's incredibly tricky. It also needs to bond really well, really quickly with the layer below it to create a strong, unified structure. It's a high-performance material, engineered for this very specific, very rapid process.
So definitely not just add water and stir. And beyond just setting quickly, what else does this special concrete need to do, performance-wise?
Well, once it's cured, it obviously needs to be strong and durable, just like regular concrete. But it also has to be very stable dimensionally. It can't shrink or expand too much with temperature changes or moisture. Otherwise, you get cracks or the layers might separate.
Like wood warping.
Kind of, yeah.
Yeah.
We talk about wood's modulus of elasticity, how much it bends before breaking and how it reacts to moisture. Engineers need to understand and control the same kinds of properties, like resistance to dimensional changes, perhaps even more carefully for these printed concretes. Because you don't have the solid mass or the formwork of traditional concrete, the integrity of each layer and the bond between layers is absolutely critical.
That sounds like some serious chemistry and engineering. Now, all this precision, it's all driven by computers, right?
Yeah.
Which brings us to digital design, building information modeling, or BIM. How does that digital plan actually become the physical wall?
This is where something called parametric solid modeling is just essential. It's a design approach where you define complex shapes not by drawing every single line, but by setting up parameters, dimensions, angles, curves.
So like variables in an equation.
Kind of. And the beauty is, if you need to make a change, say, make a curved wall slightly wider, you don't redraw everything. You just change the parameter, the variable, and the software automatically regenerates the entire design, keeping everything connected and consistent.
Ah, that sounds way more efficient for design changes.
Massively efficient, especially when you're exploring complex forms or need to make quick adjustments during the design phase. It's perfect for the kind of customization and iteration that 3D printing allows.
So these 3D computer models aren't just pictures. They're like the direct instruction manual for the printer.
Exactly. For any complex modern building, these computer-generated 3D models are fast becoming the main way everyone communicates. But for 3D printing, they are the communication. The printer is literally reading that detailed 3D model line by digital line and executing it in the physical world, layer by layer.
Incredible precision.
Unprecedented precision, really. It minimizes the kind of errors you get from interpreting 2D drawings, and it connects back to that old architectural idea from Louis Sullivan. Form follows function.
How so?
Well, historically, how you could build often limited the shapes you could design. You used straight lines and right angles because bricks and timber framing made that easiest. But with 3D printing, guided by these complex digital models, designers can create forms that much more directly express the building's purpose or aesthetic intent without being quite so constrained by traditional methods. It's like giving architects a more direct line from their imagination to the final structure.
That idea of freeing up the form is really powerful, and it leads us right into why everyone's so buzzed about this tech. Beyond just being new, there are some big promises here. Let's start with maybe the most obvious one: speed and efficiency.
Speed is definitely a headline benefit if you compare it to traditional construction. Well, we all know that can be slow, sometimes unpredictable. You hear stories, right? Like that one in House about the carpenters cutting 40 rafters and none of them fit.
Right, mistakes happen, things take longer.
Exactly. That kind of wasted time, wasted material, wasted labor. That's what 3D printing, with its automation and digital precision, aims to dramatically reduce. The machine follows the plan, it doesn't misread a measurement, it doesn't get tired.
So cutting down on that manual labor and potential for error, how does that actually speed up the overall project timeline?
It's similar to how manufacturing plants constantly try to improve their operations,
Yeah.
make them more efficient, like we read about in the goal. They want to cut lead times. 3D printing applies that thinking to construction, automating the wall building, minimizing errors, potentially running the printer for longer hours. It all aims to get the basic structure up much, much faster than laying bricks or building forms for concrete.
We're talking days instead of weeks for the walls.
Potentially, yes, for the shell. It's about optimizing the whole workflow, making timelines more predictable, streamlining that part of the process in a way that's hard to do with purely manual methods.
And building faster isn't just about getting the keys sooner, is it? It must have a big impact on the project's finances.
Oh, absolutely. Project managers live and breathe time-cost trade-off analysis. Faster construction means you can potentially cut the total project duration and accelerated cost. Think about it. Fewer labor hours for that stage, less time renting equipment, shorter financing periods for loans, less overhead for managing a long project.
Less exposure to delays from weather, maybe.
That too, all those things add up. Compressing the schedule, especially for the structural part, can lead to significant financial savings, which could potentially make housing more affordable. That's a huge driver here.
Okay, speed is compelling. What about waste reduction? That seems like another major plus, especially with the focus on green building these days.
Yeah, this ties right into things like lean supply systems in construction, which is all about minimizing waste in every form, not just physical trash, but wasted time, excess inventory, inefficiency. 3D printing hits the physical waste aspect head on.
Because it's additive.
Exactly. It only puts material where it's needed according to the design. You don't have nearly as many offcuts, scraps, or leftover materials that are so common in traditional building when you're cutting lumber or drywall to fit.
Yeah.
Construction sites generate a lot of landfill waste. This could drastically reduce that.
So less dumpster filling. How does that fit into the bigger picture of green building?
It's a really natural fit. Green building aims to use fewer resources, reduce waste and negative environmental impacts, and decrease life cycle costs. Printing on demand with precise material placement ticks a lot of those boxes. Less material transported, less material wasted on site, it contributes directly to a more sustainable process. And looking ahead, the potential is even greater for things like waste recycling, waste reduction, emissions mitigations. You could imagine using recycled materials in the concrete mix itself. Printing locally reduces transportation emissions. It all contributes to those bigger goals like achieving net zero energy or net zero water buildings, homes that are much lighter on the planet. It's about building smarter, not just faster.
Building smarter, greener homes.
Okay.
You touched on this before, but let's talk more about the design freedom, the ability to create complex shapes. What does that unlock for architects?
This is where architects get really excited. Traditional methods often push you towards, let's be honest, boxes. Flat walls, right angles.
Yeah.
Because curves, complex geometries, they're difficult, labor-intensive, and expensive to build with bricks or standard framing.
Right.
3D printing kind of blows those limitations away. It can create complex shapes, flowing, curvilinear designs almost as easily as it can print a straight line. This gives designers a whole new toolkit, a new vocabulary, as one source puts it, to work with. Forms that were just structurally or economically impractical before are suddenly possible.
So, like breaking free from the straitjacket of traditional techniques, are there historical echoes of this? Times when new tech changed architecture?
Definitely. Think about architects like Palladio, exploring new ways to organize interior space or create novel ideas of massing, or Alberti writing about the beauty of complex vaulted roofs divided into panels or across different ways. Architects have always pushed the boundaries of what's possible with the tools they had.
And 3D printing is the new tool.
It's a powerful new tool. It allows for the kind of intricate, mathematically complex forms that maybe Palladio or Alberti dreamed of, but couldn't easily realize without incredible expense and highly specialized craftspeople for every single curve or vault. Now, the complexity is handled by the digital model and the machine, freeing the designer to focus more on the aesthetic or functional aspects.
So it's not just big, swooping curves, but maybe finer details too.
Yeah.
Texture, customization.
Absolutely. You could program the printer to create specific surface textures as it builds the wall, maybe mimicking traditional brick textures or creating entirely new patterns. Think about the variation in historical stonework. Now you could achieve that kind of visual richness mechanically, customized for each project, maybe given each wall, without necessarily adding huge costs. It opens up really interesting aesthetic possibilities beyond just the overall shape.
Okay, the potential is clear, faster, greener, more creative. But like any big innovation, there's always the but. Let's get into the reality check. What are the major roadblocks keeping 3D printed houses from going mainstream right now? Let's start with the structure itself reinforcement.
Right, this is probably the single biggest technical hurdle. Concrete is great under compression when you squeeze it, but it's brittle, as the sources say. It doesn't handle tension-pulling forces very well at all. It cracks.
That's why we use rebar, right? Steel bars inside the concrete.
Exactly. For centuries, we've used steel longitudinal and web reinforcement to give concrete the tensile strength it lacks. That rebar takes the pulling forces, stops the concrete from cracking apart under bending loads or differential settlement, or even things like wind or earthquakes. It's absolutely fundamental to safety and durability in traditional concrete.
So how do you get rebar into a wall that's being extruded layer by layer by a printer? It seems tricky.
It is very tricky, and it's the critical challenge everyone's working on. How do you effectively integrate that steel reinforcement, or maybe newer composite reinforcements, into this additive process? You can't just easily place a rebar cage like you do before pouring concrete into a form. People are trying different things, having robotic arms insert steel segments between layers, developing special concrete mixes with reinforcing fibers already mixed in, printing hollow cavities and then filling them with rebar and grout later. But finding a method that's reliable, efficient, and easily verifiable for safety inspections, that's the puzzle. Without a proven, scalable solution for reinforcement, widespread adoption is impossible.
Yeah, safety first, absolutely. Okay, moving from the physical structure to the paperwork, building codes, that sounds like another potential nightmare for a new technology.
It's a huge one. Building codes are by nature based on what we know works, based on decades, even centuries of experience with traditional materials like wood, steel, masonry, and standard concrete construction techniques.
They're designed for the known quantities.
Precisely. So when you come along with something totally new like additive manufacturing for walls, the existing codes often just don't apply directly. There aren't specific sections for 3D printed concrete strength, or how to assess fire ratings for layered walls, or how windows and doors should be properly secured and sealed within these novel structures.
So builders are kind of in limbo.
They often have to go through a much more complex approval process. Maybe seeking special permits, funding extensive independent testing to prove their specific system meets the intent of the code, even if it doesn't fit the prescriptive letter of it. It's slow, it's expensive, and it creates uncertainty. Until there are clear, widely accepted standards and updates to the building codes that specifically address 3D printing, it remains a major barrier to scaling up. It also ramps up the need for really thorough risk management because you're dealing with unknowns.
A bureaucratic maze on top of the technical challenges. Okay, and you reminded us earlier, the printer usually just does the walls. That brings up integration, right? Making this new wall system play nice with all the traditional stuff.
Yes, the supply chain and integration challenge. It's easy to forget, but a huge part of building a house is everything except the structural walls. Insulation, vapor barriers, finishes, the roof system, plumbing, electrical, HVAC.
All the stuff that makes it livable.
Exactly. And all those systems need to be installed within or attached to this 3D printed shell. And the tradespeople doing that work, the electricians, the plumbers, the roofers, they're used to working with traditional wood frames or concrete blocks.
They know where the studs are, how to run wires.
Right. Now they have to figure out how to work with potentially hollow, curved, uniquely textured concrete walls printed by a machine. How do you attach things? How do you run utilities through the cavities if they exist? It requires different techniques, different fasteners, maybe different planning up front.
So coordination becomes even more critical.
Immensely critical. You need tight coordination between the printing team and all the subsequent trades. Everyone needs to understand how this new element works and how their specific job integrates with it. It's a learning curve for the entire project team. And don't forget the materials themselves. That specialized concrete mix isn't something you just order like regular cement. You need a reliable supply chain for these unique, high-performance materials, manufacturing, delivery, quality control. Any disruption there could stop a project cold. Getting materials on time to project sites is vital in lean construction, and even more so when the core material is so specialized.
Okay, technical hurdles, codes, integration. What about the people? The workforce. Is there resistance or a need for totally new skills?
The human element is huge. As the BIM handbook points out, adopting new tech like this often finds that human resource considerations are the leading concern. Success depends entirely on the skill and goodwill of the people using the technology.
So you need trained operators for these complex printers, obviously.
Yes, but it's broader than that. You need designers who understand parametric modeling specifically for printing. You need material scientists. And crucially, you need the traditional tradespeople to adapt and learn how to work with these new structures.
It's not necessarily about replacing jobs, but changing them.
Exactly. Subcontractors need training on how the building project differs from a conventional one. A plumber still needs plumbing skills, but now they might need to understand how to interact with a digitally fabricated wall system, maybe even collaborate during the printing phase to embed pipes. It requires upskilling, adaptability, and, frankly, a willingness to embrace change, and makes you think about craftsmanship. It's not disappearing, but it's evolving. The skill might shift from purely manual dexterity to understanding complex systems, managing digital workflows, operating robotics, ensuring quality control in a highly automated process. It's a new kind of skilled work, blending digital literacy with construction knowledge.
That's a really interesting way to frame it, the evolution of craft. So, despite all these challenges we've laid out, there are clearly people, pioneers, pushing this forward. Why? What's the big picture goal, especially when we think about things like the housing crisis?
Well, at its core, it connects to a fundamental human need, the desire for a stable home, a dwelling place devoid of fear, as one source eloquently puts it. The global housing crisis, the lack of affordable, available homes in so many places, creates a powerful motivation to find radically faster, cheaper ways to build.
So 3D printing is seen as a potential tool to tackle that massive problem.
Very much so. It's not just cool tech, it's being explored as a way to provide dignified shelter more quickly and affordably. If you can significantly cut construction time and labor costs for the structure, you could potentially make a real dent in the affordability gap.
But for it to really be a solution, it can't just be innovative. It has to be economical, right? Economy's king in construction, usually.
Absolutely. Ultimately, it has to be cost-effective, as Designing Reality notes, not just for high-end custom homes, but for individuals and communities. The promise is their automation, less waste, faster builds should theoretically lead to lower costs per square foot.
Are we seeing that yet?
We're starting to see examples. Companies like Icon, Alquist, and others are demonstrating projects built significantly faster and claiming cost savings compared to traditional methods, especially for simpler structures or in developing regions. The goal is to drive those costs down further through scale and technological refinement until it becomes a genuinely competitive or even cheaper alternative. And this ties into that Fab City idea too, cities being globally connected yet locally productive. Imagine communities using local materials, maybe even recycled waste or earth-based mixes, combined with digital design shared globally to print their own housing solutions.
Wow, like local production hubs for houses.
Potentially. It could make construction more generative, building local capacity and resilience, rather than purely extractive, relying on distant resources and complex supply chains. That's a powerful vision for sustainable development.
That local production idea is fascinating. Looking even further ahead, how does this fit into the whole smart city concept? Are these just dumb structures, or can they be more integrated?
The potential for integration is huge. We're heading towards smart cities where buildings, infrastructure, devices, and people are all interconnected. 3D printing is uniquely suited for this because it's digitally native.
How so?
You can design conduits for wiring, sensors, fiber optics, even plumbing directly into the walls as they're being printed. Instead of drilling holes and retrofitting later, you embed the infrastructure from the start.
So the building itself is born smart.
Essentially, yes. It allows designers to become, as one source puts it, choreographers of dynamic and adaptive forces. Using principles from cybernetics, the science of control and feedback, you could create buildings that genuinely learn from and coexist with their occupants.
Like adjusting lighting or temperature automatically based on who's in the room or the time of day.
Exactly. Creating truly dynamic spaces that respond to needs, optimize energy use, and improve comfort, all enabled by the precision and control offered by embedding systems during the printing process. It moves buildings from static shells to responsive environments. But at the end of the day, whether it's cost savings, sustainability, smart features, or just building faster, it all comes back to delivering value. That's the ultimate driver. Is this technology providing a tangible benefit, financial, social, environmental,
It
experiential?
has to prove its worth across the board.
Right. For 3D printing to really take off, it needs to consistently demonstrate that value proposition, showing it's not just a novel way to build, but a better way to build in multiple dimensions.
It really feels like we're watching that transition happen now, from futuristic idea to practical reality, thanks to these
Yeah.
pioneers.
Definitely. This deep dive was about looking at those practical realities, asking the tough questions. The companies leading the charge are actively tackling these hurdles we've discussed: the reinforcement, the codes, the supply chains, the workforce training. It's messy, it's challenging, but it's also incredibly exciting to see engineering and innovation trying to overcome these obstacles for such a potentially huge payoff. Building a better future, quite literally. Hashtag TacTech outro.
Wow, okay. That was quite a dive into the world of 3D printed homes. We've seen how it works mostly printing the concrete walls for now, and how it needs to mesh with traditional building methods.
Yeah, and the potential benefits are really clear, aren't they? Speeding up construction, cutting down significantly on waste, and opening the door to some really complex, exciting architectural designs, all driven by digital tools and a push for more sustainable building.
But as we explored, the path forward isn't exactly smooth. There are major hurdles. Getting the structural reinforcement right is critical.
Absolutely fundamental. And then navigating the building codes, getting regulatory acceptance, that's a huge undertaking. Plus, developing the whole supply chain for these new materials and figuring out how all the different trades work together seamlessly on site.
And let's not forget the people training the workforce, adapting skills, getting everyone comfortable with a new way of building. It's a complex puzzle.
It really is a fascinating mix of high-tech potential and very down-to-earth challenges.
So here's something to chew on. If this technology really matures, if a printer can build walls faster, cheaper, with less waste, and create previously impossible shapes, what does that ultimately mean for the traditional builder, the carpenter, the mason? Does their role change fundamentally?
And maybe even how does our idea of home change when it starts as lines of code before it becomes layers of concrete? What kind of new challenges, but also what amazing new opportunities might pop up if we can genuinely start to print our way out of housing shortages, or at least make a serious impact? What will those printed neighborhoods actually look and feel like?
Lots to think about as this technology continues to evolve right before our eyes.